In this lesson, we will delve into the content of Task 1.2 Inches Project 1, which covers the types of milling cutters, geometric angles, and ISO coding. You can imagine milling cutters as the sharp tools in a craftsman's hand. Different types of milling cutters can accomplish a wide variety of machining tasks, while the geometric angles of the cutters determine their cutting performance. ISO coding provides us with standards for accurately selecting and using milling cutters. Next, let's unveil the mysteries of milling cutters together. In the field of metal cutting, milling is a very important machining method, and the milling cutters are the key tools for milling operations. We will now provide a detailed explanation from three aspects: types of milling cutters, geometric angles, and ISO coding. Types of milling cutters. There is a wide variety of milling cutter types, each suitable for different machining scenarios. Cylindrical milling cutter. Cylindrical milling cutters are primarily used for machining flat surfaces on horizontal milling machines. The teeth are distributed on the cylindrical surface and can be classified into straight teeth and helical teeth based on their shape. The cutting edges of straight-tooth cylindrical milling cutters are parallel to the tool's axis. During cutting, the cutting thickness of each tooth varies, which can easily cause impact and result in less stable cutting. In contrast, the cutting edges of helical-tooth cylindrical milling cutters are spiral-shaped. During the cutting process, the teeth gradually engage and disengage with the workpiece, resulting in smaller variations in cutting force, more stable cutting, and higher surface quality of the machined workpiece. For example, when machining flat surfaces with lower precision requirements, straight-tooth cylindrical milling cutters can be used. However, for flat surfaces requiring higher precision, helical-tooth cylindrical milling cutters are more suitable. Face milling cutter. Also known as an end mill, the face milling cutter is primarily used for machining flat surfaces on vertical or horizontal milling machines. Its teeth are distributed on the end face of the cutter body and can be either integral or indexable inserts. Indexable insert face milling cutters have advantages such as long tool life and easy insert replacement, making them widely used in modern machining. Face milling cutters have a larger diameter, which results in high cutting efficiency and good surface flatness. For instance, when machining the flat surfaces of large mechanical parts, face milling cutters can fully demonstrate their advantages. End mill. The end mill is a commonly used milling cutter with teeth distributed on both the cylindrical surface and the end face. End mills can be used for machining flat surfaces, stepped surfaces, grooves, and more. Based on the number and shape of the teeth, end mills can be further divided into coarse tooth end mills and fine tooth end mills. Coarse tooth end mills have fewer teeth and larger chip pockets, making them suitable for rough machining. Fine tooth end mills have more teeth and sharp cutting edges, making them suitable for finish machining. In mold manufacturing, end mills are often used for machining the cavities and cores of molds. Keyway cutter. The keyway cutter is specifically designed for machining keyways on shafts. It resembles an end mill in appearance, but has fewer teeth and larger chip pockets. The cutting edge at the end of the keyway cutter passes through the tool's center, allowing for direct axial feeding to mill the full depth of the keyway in a single pass. In mechanical manufacturing, the keyway is a common connection structure, and the use of keyway cutters ensures the precision and efficiency of keyway machining. Form milling cutter. The cutting edge of a form milling cutter matches the contour shape of the workpiece being machined. It is used for machining surfaces with specific shapes, such as gear teeth profiles and splines. The design and manufacturing of form milling cutters are relatively complex and costly, but they offer high machining precision and efficiency. For example, in gear machining, using a form milling cutter allows for the direct milling of gear tooth profiles, significantly improving machining efficiency. The geometry of milling cutters The geometry of milling cutters has a significant impact on the milling process and the quality of machining. The main geometric angles of a milling cutter include the rake angle, relief angle, major cutting edge angle, minor cutting edge angle, and helix angle. Rake angle. The rake angle is the angle measured between the rake face and the reference plane in the orthogonal plane. The size of the rake angle affects cutting force, cutting temperature, and tool life. Increasing the rake angle can reduce cutting deformation, cutting force, and cutting temperature. However, if the rake angle is too large, the strength of the tool decreases, making it more prone to wear and breakage. Generally, when machining ductile materials, a larger rake angle can be used, whereas for brittle materials, a smaller rake angle is advisable. For example, when machining aluminum alloys, the rake angle can be set between 15 degrees and 25 degrees, while for cast iron, the rake angle is typically set between 5 degrees and 10 degrees. Relief angle. The relief angle is the angle measured between the flank face and the cutting plane in the orthogonal plane. The purpose of the relief angle is to reduce friction between the flank face and the workpiece, thereby extending the tool's lifespan. If the relief angle is too large, the strength of the tool decreases. If the relief angle is too small, friction increases and cutting temperature rises. The size of the relief angle is usually selected based on the material being machined and the cutting conditions. Generally, a smaller relief angle is used for rough machining, while a larger relief angle is used for finish machining. Principal cutting edge angle. The principal cutting edge angle is the angle measured between the projection of the main cutting edge on the reference plane and the feed direction. The size of the principal cutting edge angle affects the distribution of cutting forces, as well as the cutting width and cutting thickness. Reducing the main cutting edge angle can increase the cutting width and decrease the cutting thickness, improving the tool's heat dissipation conditions and extending tool life. However, if the main cutting edge angle is too small, it can increase the radial cutting force, which may lead to vibration. Common main cutting edge angles include 45 degrees, 60 degrees, 75 degrees, and 90 degrees. When machining slender shafts, a tool with a 90 degrees main cutting edge angle is often chosen to reduce radial cutting force. Minor cutting edge angle. The minor cutting edge angle is the angle measured between the projection of the minor cutting edge on the reference plane and the opposite direction of the feed. The purpose of the minor cutting edge angle is to reduce friction between the minor cutting edge and the machined surface, thereby improving the surface quality. The minor cutting edge angle is generally set between 5 degrees and 15 degrees. Helix angle. The helix angle is the angle measured between the principal cutting edge angle and the reference plane within the cutting plane. The sign, positive or negative, and the magnitude of the helix angle affect the flow direction of the chips and the strength of the tool. When the helix angle is positive, the chips flow towards the surface to be machined. When the helix angle is negative, the chips flow towards the machined surface. In rough machining, a negative helix angle is often used to enhance the strength of the tool. In finish machining, a positive helix angle is typically chosen to prevent chips from scratching the machined surface. ISO code for milling cutters. The ISO code is a tool coding system established by the International Organization for Standardization used for the unified identification and management of milling cutters. The ISO code includes information about the type, size, and precision of milling cutters. Through the ISO code, we can accurately select and use milling cutters. An ISO code typically consists of multiple parts, each representing different meanings. For example, a typical ISO code may include a tool type code, size code, precision code, and so on. The tool type code is used to indicate the type of milling cutter, such as cylindrical milling cutters or face milling cutters. The size code is used to represent size information, such as the diameter and length of the milling cutter. The precision code is used to indicate the manufacturing precision of the milling cutter. By consulting the ISO code manual, we can select the appropriate milling cutter based on machining requirements. In precision milling, there are almost stringent requirements for the dynamic balance and the clamping accuracy of the tool system. Poor dynamic balance can lead to vibrations during the milling process, affecting machining accuracy and surface quality, and may even damage the tool and machine. Insufficient clamping accuracy can cause a deviation between the actual cutting position of the milling cutter and its theoretical position, which similarly affects machining accuracy. This requires us to approach the machining process like craftsmen, meticulously attending to every technical detail, striving for the highest quality in machining, and embodying the spirit of continuous improvement and excellence. In this lesson, we primarily covered the knowledge related to milling cutter types, geometric angles, and ISO codes. Regarding milling cutter types, we introduced various types such as cylindrical milling cutters, face milling cutters, end mills, keyway milling cutters, and form milling cutters, along with their applicable scenarios. In terms of the geometric angles of milling cutters, we learned about the definitions and functions of the rake angle, relief angle, principal cutting edge angle, minor cutting edge angle, and helix angle, as well as their impact on the milling process and the machining quality. In terms of ISO codes, we learned that the ISO code is a tool coding system established by the International Organization for Standardization, providing a standard for accurately selecting and using milling cutters. At the same time, we also emphasize the importance of embodying the spirit of continuous improvement and excellence in precision milling, meticulously attending to technical details, and striving for the highest quality in machining. I hope that through this lesson, everyone has gained a deeper understanding of milling cutters and will be able to correctly select and use them in future studies and work.